So we're here at the 2013 Planetary Defense Conference, and I'm here with Dr. David Dearborn. Do you want to introduce yourself to the audience?
Well, my name, as you heard, was Dave Dearborn. I'm a scientist working at Lawrence Livermore National Lab. We work on defense issues, and I'm here principally because I'm doing research on the nuclear option for deflecting asteroids. Okay.
And discussed here and then in general, there's a lot of different options discussed about planetary defense. It's obviously a concern we're going to have to deal with at some point. We're probably going to have to stop one of these asteroids from coming in. And there's a lot of discussion about what methods could be used to slow down the asteroid, move it out of the way to ensure it doesn't hit the Earth, ranging everything from pulling on it gravitationally, attaching rockets to it to push, a whole range of options, running something into it. And so what do you think the importance of the nuclear option, so-called, is, the use of peaceful nuclear explosives for this work?
The nuclear bond is the strongest thing in nature, and that's basic physics. And
sure.
The result is that if you can package that nuclear energy and release it, it is the most pound-for-pound greatest energy you can transport. So long as we're wanting to interact with asteroids a long ways out in space, the question really is how much mass you can lift off of the Earth and put in space. Big deep space missions, the satellites that we send out there go out with 4 or 5 tons commonly. And so if you have a mission that requires you to send 1,000 tons to deep space, that's a challenge that we're not up to yet. Right. Nuclear, in a mission that requires a lot of energy, which suggests larger asteroids,
right.
The nuclear allows you to transport the energy you need and get it to an asteroid so that you can use that to slow the asteroid down or speed it up, whichever direction most directly removes it as a threat.
So it basically comes down to a question of energy density per weight, more or less.
As long as getting into space is expensive, the nuclear is going to be an option that has to be considered. And if you can, the other thing to think about is there's 2 regimes of stopping an asteroid. Because of the surveys, we now have a much better chance of discovering an asteroid and realizing that's a threat 50 years from now, 80 years from now. And if you can discover that and it's enough of a threat, you can track it and get the orbit precisely enough that it's the probability of collision worries you, you can go out and perturb that orbit. And if you're 30 years out, the speed change that you need to make it miss the Earth and no longer be a threat is less than a centimeter a second. It depends a bit on the orbit, but if it's less than a centimeter a second, well, that's wonderful. Yeah. Let's do it out there. And if it's a small one, an impactor can do it.
Basically running a spacecraft into the asteroid.
Basically loading a spacecraft up with bowling balls and running them in. And that, I believe, can certainly work up to sizes of 200 and 300 meters. And 200 and 300 meters would be a bad thing if one of them were to fall on Texas, it would be a bad thing for the whole state.
Right.
So it's not a minor thing, and the impactor technology could really help us to there. Once it gets somewhere above that, you would have to launch fleets of these impactors. And these impactors also, people often talk about 1 to 10 tons. And so again, you're talking a larger rocket to be able to get that much mass out to deep space. So that's a lot of work. The nuclear option is a lot lighter payload. You can go out and provide even more impulse to deflect the asteroid. So that's the case where we've discovered it with a long time to go. There is the other side of that, and as the search efforts to find asteroids is going deeper and deeper, we're going to one of these days probably find something that's coming straight at us. And in fact, that's already happened once. There was the incident in 2008 over the Sudan where it was discovered with 19 hours to go. And fortunately, it's a relatively small asteroid, much smaller than even the Chelyabinsk event. It broke up 30 kilometers up in the atmosphere. Pieces of it were found on the ground, no damage, not even the shock coming down in that case. So that was merely a kiloton or two at high altitude. So, in sometime in the future, we are likely to discover one that is bigger than the Chelyabinsk meteor coming at us, and we may have less time to react. And at the moment, let's say, if we had all the pieces technically ready that we could just launch, one of the talks you saw yesterday by the fellow from Iowa State was very complimentary to a calculation I'd done some years back, in which an object of order a couple hundred meters is broken up by a nuclear explosion at the surface, and the debris spreads out so much that it misses the Earth. You wouldn't do this in the low Earth orbit.
Right.
If you do it then the people who say, oh, you'd spread out the damage and it would be bad. Yes, that would be a foolish thing to do and wouldn't want to do that. But if you reached out 10 or 15 days prior to impact and broke it up robustly at that point, 99% of it or more can miss you. And the pieces that do hit, as in his model, were too small to penetrate the atmosphere. And so, he said, go out and enjoy the meteor shower. It'll be a good one. So that's the other regime where it's discovered late.
Right.
Now the fact is we don't have a rocket sitting on the pad ready to go with a bus that can carry either an impactor or a nuclear explosive, and in the absence of that, the question is, well, starting from scratch today, how quickly could we make one? And without any effort, the time scale between for building up rockets, they're doing it all the time. So depending on where they are in the process of building up a rocket for a launch and what type of rocket it is, it could be 3 to 6 months to have a rocket. The nuclear explosive that you'd need, we have stored away, for refabrication or maintenance. We can grab one, and it can be ready fairly quickly. What we don't have is the piece that would carry it from the end of the rocket when the rocket launches and throws it out there. It has to then have a piece that guides it to the asteroid and measures as it's coming in the distance away from the asteroid so that it goes off at the right distance, be that a little ways away for a standoff or up very close for a fragmentation. You will have seen at this conference at this point 3 proposals for impactor missions. That technology is exactly the technology that would be needed. So if they do indeed fly one of those impactor missions, they would be testing the equipment needed to throw bowling balls at it. Well, you can take out 5 of the bowling balls or whatever and put in a nuke.
Right.
And the same mission could fly with a lot more potential result.
Right.
And so that's...
Well, I'd just say the short warning time does seem like probably one of the most likely scenarios. I mean, you take the case of 2012 DA-14, which flew between the Earth and that might be a good example. It was about the size of the one that they think hit over Tunguska. Could take out an entire city or metropolitan area. We found that about a year before it flew by the Earth, and it just barely missed us.
And so a real question is, given that we have not flown an impactor mission yet, and we don't have a design for that bus portion, much less an extra one sitting on the shelf, how long would it take us to design that and get it off?
Right.
And, if it were a national emergency. And there's not a lot of optimism that it could be done inside of a year at the moment. I like to hope that we have some people that are willing to work nights and weekends in that case.
Right.
It's going to take more than that.
Right. So basically, there's these two scenarios you described where nuclear power would basically be necessary to defend the Earth. The one being a short-term scenario when you need to disperse the object, probably a relatively smaller object, and you disperse it so it doesn't impact the Earth and the material misses generally. And you said the other one would be generally for larger objects. You said maybe on the order of above 200 or 300 meters in diameter.
Right. I think that 200 or 300 meters can be handled by an impactor. And you saw a JPL example of a mission like that in which you had a certain percentage of threat 10 years out. And is that enough to launch a whole mission? Well, if you wait longer, the percentage of threat goes up, and eventually you get to a place where you know it's going to hit. At that point, if you know it's going to hit in a stripe across the Earth, you might say some of those places are bad. Let's stop it, and especially if it's over 100 meters. Just about anywhere it lands is going to cause some problem. And in those cases, when can you have a launch and an impactor do the job? In the case that they were showing the other day, you got to 4 or 5 years out, and the ability of an impactor to deflect it basically went down to nothing. And so you were going to be hit at that point. At that point, if people haven't stepped forward and sent an impactor mission, the only solution is a disruptive nuclear mission. And you would still like to do that as early as you can. But again, for a couple 100-meter object, you have to reach out to where that asteroid will be 10 days before impact, which is far beyond the orbit of the moon. And you have to disrupt it there so that there's time, even with the many meters a second dispersion velocity you have, that the debris expands to a cloud that's very large compared to the size of the Earth. So the Earth will go through that. One of the other models shown yesterday by Paul Miller, who's also from the lab and leads a lot of the effort there, showed a 50-meter iron that was exposed to a megaton explosion at its surface.
An iron asteroid.
An iron asteroid, yes.
So solid metal.
Solid hunk of metal, about 50 meters across. And so if you've seen the Barringer crater, think that.
Right.
And the megaton, 50 meters across, broke it up into pieces that were all too small to really penetrate the atmosphere at any speed. And so it would have greatly reduced the threat to the Earth if you could reach out. And even in that case, you don't want to do it just as it's approaching the Earth. You'd like to do it many, many Earth radii out. And better yet, do it beyond the orbit of the moon so that, again, the pieces, most of them miss the Earth, whether they'll go into the atmosphere or not.
Right.
They also miss the television satellites then.
Right.
Think how bad people would be if we didn't.
Then you really get people upset,
Yeah,
right?
you would really get people upset then.
And the other scenario you described is what you were calling a standoff explosion, which is a little bit of a different scenario, correct?
Right. The standoff explosions, what you would do if there is, some decades to impact. And in those cases, the speed change you're wanting to give it is, again, of order a centimeter a second. And if the asteroid is large, if it's 1 kilometer in diameter, it weighs 1 billion tons. And if you run even a 10-ton impactor into it, it kind of goes, and just keeps going. It doesn't change its speed very much.
Right.
So you need something that can evaporate about 10,000 tons, turn about 10,000 tons of surface into a gas.
Wow.
And that you can do with a nuclear package that's carried in on something a lot less massive than that impactor. And you vaporize a lens of material on one side that pushes the object and changes its orbit. And a centimeter a second is not very hard. It could easily be done with yields that we have available today. It doesn't require any development of new nuclear devices, it is a doable thing with the currently existing nuclear explosives.
So you basically detonated a certain optimal height above the surface that sends the radiation down to the surface, which
it creates. Yes, I'm sorry, we wanted the standoff part. By detonating at some distance above the surface, if you detonate very close to the surface, you're heating a very small area and you're pushing it very hard, and that sends a tremendously strong shock into the thing and stands a good chance of disrupting it. If you stand back some distance, you are heating at to a lesser degree, because most of the radiation, most of the X-rays are going off into space.
Right.
But the part of it that you hit evaporates, and you evaporate that much soil at the surface, and
over a large area.
Over a large area, and that gives a gentle, broader push, so that the asteroid is not so much jarred to want to come apart, but mostly given a push in some direction.
So all that layer of surface then blows off as like a thrust.
The surface all blows off. The part that evaporates comes off at kilometers a second, and so you're really only trying to change the bulk density or the bulk material of the thing by a centimeter a second. So the stuff that comes off at a kilometer a second is now going nowhere near the Earth. There will also be some rebound of material, and you'll be producing a crater on that side, and some of the ejecta will also come off at lesser speeds, but still many meters a second for a lot of it, and that increases the push. But most of that debris then misses the Earth. And in our simulations, after we do a deflection mission and we push on an asteroid, we take both the body and all the debris and put it on different orbits to see, is there anything that threatens the Earth? And for very large bodies, the fraction that would hit the Earth would be 100,000th of the material of the entire asteroid or less. And so that again becomes something that probably burns up in the atmosphere. And it is certainly better than a kilometer-sized body hitting, which is not just a regional disaster, but it's a global problem at that point. Even if it hits on the far side of the globe, you're going to have problems in the coming year from that.
Right. And then there was some discussion about some of the uncertainty with the composition of the bodies. How exactly will the asteroid react to either getting hit with a kinetic impactor or a nuclear explosive? And there's some concern that until we know what exactly the body's made out of and how it will react, that'll determine how efficient these different options are. When
we look at asteroids, we've been able to, the people who've worked in the area have done heroic work to determine the densities of a limited number, some tens at this point, of asteroids. And to get that, they've had to get the mass measured either when it passed a planet, seeing how it bent, or sending a space probe past it and seeing how the space probe was bent in its orbit, and have measured the size and shape of the asteroid. And of the ones we've seen, there are some objects out there that have densities 2.5 to 3.5 grams per cubic centimeter, and which is
very high density, correct?
That's high density. That's the density of the solid rocks, and so those guys are objects that sort of like what you feel underfoot. They have that kind of texture and density. There are other bodies like Itokawa, the asteroid Itokawa that the Hayabusa mission went to, and that one, you remember, looked like a peanut, kind of the whole thing, but it looked very rubbly, and the density on that one is 1.9 grams per cubic centimeter, which is, if you get a load of gravel delivered to your house and you want to say what's the density of that pile of gravel, that's what Hayabusa has. Now, it may have some bigger rocks and some smaller rocks in there, but it's a very rubbly object. And there are other objects out there, and one example of them is Matilda, that appear to have relatively low densities, potentially lower than 1 gram per cubic centimeter. And the examples of that on the Earth might be something like pumice. And all of those materials react differently when you apply an impulse. So if you're wanting to change the orbit of the asteroid, you're wanting to push it some. And so you give it an impulse, and they respond differently to an impulse. The more porous materials, things like pumice, crush up, and there's very little rebound, so very little additional material is thrown off.
That's what you're describing with the cratering effect, where you can get an additional boost because some of the materials
thrown back off. That's exactly right.
Yeah.
And so you might still get a bit of a crater, but it'll be a very different crater and mostly just crushed up material. And so you have, as you go from those lowest density asteroids to the highest density pieces, you have quite a range of how they're going to behave. And, we have to be prepared for whatever asteroid comes along. And in the case of one that was discovered with some decades to go, by far the most the first thing to do is to send out a discovery mission that goes and measures that asteroid, gives you some information about its detailed structure, gives you some information about its density and true mass, and gives you information, everything you can learn about it, composition, so that when you try to push it with an impulse, either by an impactor or by a nuclear explosive, you will have a more controlled push. And so that will be the case for a long time, when it's discovered a long time before impact. In the case of a short time before impact, as I said, you're mostly in that case wanting to fragment the thing. And you may not have time to have a mission lead and say, oh, look, here's exactly what you've got coming. You'll have a general idea of the size because you have the brightness, but the size may be uncertain by a factor of 2. And if you go look through the JPL list of things that pass close to the Earth, the size of them, most of them, are uncertain by a factor of 2 because they were discovered much further out. And all we know about them is how much light they're reflecting towards us, but we don't know details about the surface, about how reflective the surface is. And so it could be a thing that's very large with very low reflectivity, or a thing that's much smaller with a higher reflectivity. And in that case, when you don't have time to go out and find out, you would probably throw something a little larger than you thought you needed to make sure that if it was at the larger size, it would still be disrupted in the way you wanted. If you disrupt the smaller piece faster, well, that's even better.
Right. Now, what about the question of long-period comets? Because that's, I think it's been discussed as much as the asteroid question, and there you seem to be dealing with objects that we would likely get less of a warning time because they tend to come from farther out, and they're harder to see when they're farther out. And they tend often to be larger and come in faster. And I've seen some discussion about uncertainty, even with the power of thermonuclear explosives. There's a real limit in what we could even do to defend the Earth in a likely scenario of a comet coming in.
The comets haven't been talked about here because, yes, we don't have an answer. Now, the greater percentage of the threat are probably the guys who are bad drivers in the inner solar system, the near-Earth objects, and they're sitting there going past our orbit, and no one's looking right and stopping, giving a yield. It's probably the larger portion of the problem in terms of what's going to hit us next. But comets are bad in a couple ways. One of them you alluded to, and that is that we typically don't discover them until they're in rather close in time. The comets have very long periods. There's some what we call short period comets, things like Halley's, where the period is 75 years. But most of the comets, or a lot of the comets, are not these short period comets. They're guys that come in every 10,000 years or so. And so we haven't seen them in the history of mankind, and we probably won't see them again for, man will be very different by the time we see them next.
Right.
So the comet, when it comes in, is often discovered out beyond the orbit of Mars, but it's maybe got inside of Jupiter. It's got a couple years to go, and actually we discover a lot of comets with even less time. And so when you've only got a couple years to go, there is no long time, we'll just give it a nudge and it'll miss. Okay? So that's off the table. So what you're left with is the fragmentation. And the fragmentation becomes more challenging because while the near-Earth objects do go up over a kilometer in size to, in fact, a few kilometers in size, comets tend to be big. Yeah. Not a few kilometers, 30 kilometers. And a 30-kilometer thing has 1,000 times the volume of a 3-kilometer thing. And so if I can, with a megaton, deal with a 1, 2, 3 kilometer item, I need a lot more energy to disrupt a comet. The other thing is I couldn't even launch immediately at that 2 years out and expect much effort because comets, as they come in, begin outgassing, and so there's a lot of dancing in the motion. It's not a very simple orbit like the asteroids tend to do. It's putting out these jets of gas, and those jets of gas are changing the orbit all the time. So the comet that's coming in may be a clear miss at first, but it's dancing around, and if it's going to pass close enough to the Earth, it could dance onto the Earth. And
you wouldn't necessarily know that from the initial observations.
We would not know that from the initial observations. It's not a predictable behavior. And so you're forced to want to, if you're wanting to blow this thing up, and you're wanting to do it not 2 years out probably, but some months out, you want a lot of yield. And that is probably not something that resides in the stockpile of any nation on the Earth. I'm not saying that we couldn't build something that had a lot more yield than we ever tested, but it would be a bigger challenge to reduce the threat enough that people would feel comfortable. Comets are hard.
And working at Livermore, we were discussing earlier, you had said you'd never worked on this subject with Teller directly, but you participated in some discussions with it, and I know he took up a big interest in the subject. So I wonder if you had any anecdotal accounts of Teller's view on planetary defense and the importance of pursuing this issue.
I used to eat lunch with Edward Teller, and we would talk about a wide range of things, sometimes astrophysics, sometimes defense issues, sometimes science fiction. And he was always a person that was interested in education, learning things, and he was interested in asteroids, just science in general. And so back in the 90s, and this is before the geologists were all entirely sure that there had been an asteroid that was damaging to the dinosaurs. I mean, it was a popular theory at that time, but there was still a lot of argument about that. People were beginning to say, gosh, we're discovering a lot of these asteroids. This was before the Space Guard even started. They held a conference at Livermore. Edward Teller attended, Lowell Wood attended, another director of the lab attended, the director at that time attended, and people were interested, but it was a time also of ignorance. And, the people from the nuclear community were going in, and they didn't know what it was going to take to deflect an asteroid. And so there were, questions, and I hear that Edward, when he talked to people at first, said, well, how many megatons do you need? That's not the sort of thing that a lot of academics aspire to talking about. So there was some initial miscommunication about why someplace like the lab and Edward Teller would be interested. And in this case, the people say, oh, you were just wanting to develop new bombs. And no, we have not done that. We've done our homework now, and the people on the other side should have done their homework about what nuclear output was like, but we've done ours. We know about the orbits. We know about how much you have to push. And given that, we know that things that we have already done in the past are just fine. And those outputs are well characterized. And, they are certainly more transportable by rockets than the impactors that people sometimes talk about. And given all of that, the real uncertainty is we're free to learn more about asteroids because the questions are in how asteroids respond. So impactor people and we have the same fundamental questions about structure of asteroids and wanting to learn more about it so that we can reduce any uncertainty in the result of pushing on the asteroid.
Right.
And, the lab has always been a place that was good at looking into the future and saying, what is it that we have technology for that can go out and help people? And if you go and talk to the public relations people at the lab, they'll be very happy to show you lots of non-defense related things that we have done as well as defense related things. But the government largely pays us to keep a special eye on those things related to defense. And so as it became recognized that asteroids were a threat and that there was some use in defending the Earth, and the terms planetary defense were coined, and I think Lindley Johnson is the one who coined that from a 1993 paper that he wrote on the subject. And it became a thing that people at the lab were interested in. At first, it was a thing that the scientists at the lab as individuals said, wow, I'll go to those meetings too. And, when people say things that are kind of silly, oh, you can't use a nuclear explosive, it will not push. Well, it doesn't have any momentum in it. Well, it doesn't have any momentum in it, but once it heats up and vaporizes one face of the asteroid, that material comes off like a rocket, and it has lots of momentum. You can push real well with it. So, the people say you can't push. People say you can't control it. It'll push too hard. You'll break it up. Well, you can break it up if you want to, but if you stand off a little ways, if you've got some idea of the mass and you stand off a little ways, you'll not break it up. You give it an impulse to change its speed, just the amount to make it a safer orbit. So that's not a threat. You had the New York Times quoting a fellow saying, and it'll all be radioactive. And no. I would not like to stand next to the nuclear explosive when it went off. That would be a bad place. But the material from the nuclear explosive mostly goes out into space and dilutes itself and gets swept out of the solar system in the solar wind and will never come anywhere near the Earth unless you're doing it on the Earth. And the material at the surface that's heated up can be weakly irradiated, and it really wouldn't be very radioactive. But even that material is now a vapor and goes off into the solar system and is spread out. If you're talking about a 1 kilometer asteroid, be a little more concerned on the ton or so of uranium that's in it. If you're worried about radioactive, it's that's what's radioactive.
Maybe one last question, maybe to return to the beginning on the energy density available with nuclear, and very concerned about the bad rap that nuclear tends to get somewhat irrationally. And you look at the potential benefits. You've elaborated obviously a lot the question of defense and the defense applications for asteroids and comets. But also it pertains to things like propulsion systems. Having a higher energy density can give you a much greater capability to move around the solar system. Or there's even things, extensive studies on engineering with peaceful nuclear explosives and be able to move material. It just gives mankind such a greater capability for an array of things. I don't know if you have any general comments on the importance of that.
Well, the problem that nuclear has had is it came into existence in a war, and it was developed as a weapon. People knew from early on that there were other uses that nuclear could be put to, and I will point out that they did have a problem in Japan at the reactor, but the number of people hurt and killed and the damage done due to the reactor problems were minuscule compared to the tidal wave. And so nuclear has potential. You mentioned nuclear propulsion. Yes, if you wanted to make the outer solar system more reachable by heavier loads, nuclear propulsion has some possibility. I hope that as the world evolves, we'll get to a place where nations are a lot less threatened by their neighbors, that nuclear explosives used as weapons are less in people's minds, and that they will be able to take a better look at how to properly utilize physics. It's nature. I mean, it is almost unnatural to pretend it doesn't exist, and that they will see other things that nuclear, both fission and fusion, can be used for. So that's, I hope, for the future.
Okay. Well, I thank you for taking the time. Do you have anything else you want to add?
No, I'm happy. I'm glad that you're interested in the subject, and please keep watching.
Okay, thank you very much.